Hello friends, this is Dr. Siva Nagaraju from IARE. Today we are going to discuss about the probability of error in ASK, PSK and FSK. In the last video we discussed about the ASK, PSK and FSK modulation techniques. Now we are going to find the probability of errors, how much error will be generated from these three modulation techniques we are going to discuss. Okay, coming to the CO. So this module belongs to CO4, and the CO4 is analyze the digital passband communication schemes using modulation demodulation process. So here we are going to analyze this passband schemes. So passband is nothing but modulation. So we are going to modulate the signal with a carrier for transmitting the signal in a radio link. So basically we are having ASK, amplitude shift keying, PSK, phase shift keying, and FSK, frequency shift keying. So these are the basic modulation techniques in binary. Okay, whereas in MR we are having QPSK is having, but in this session the error probability we are taking about only ASK, PSK and FSK. Okay, let us start the session. So the first probability of error of PSK we are considering. So why? Because PSK it is easy to understand. For that we are going in a better way to understanding taking the PSK. So in PSK, the first expression is x1 is equal to integral 0 to tb x of t pi 1 of t. So we know that what is pi 1 of t? Pi 1 of t is nothing but basis function, orthonormal basis function. So this basis function is used in the transmitter. We know that S of t. S of t is the modulated signal. Modulated signal. So which is equal to root EB pi 1 of t. Pi 1 of t is the basis function. So here you can say this is also called as a coherent version. Why? Here we use the same basis function for recovering the message signal. So this we can call as coherent detection. So here x of t. X of t is the received signal. Why? Here S of t is nothing but the modulated signal. So this modulated signal is transmitted in the radio link or channel. So the noise is going to add it with this signal. So N of t we can call as the noise. So the noisy signal is received by the receiver, but in this assumption N of t we are not considering, but the X of t is the received signal. X of t is the received signal, and X1 is the observation vector. Why? Whereas similar we're having the signal vector in signal space diagram or signal constellation diagram, we can see that this is my basis function and this is the border and this is root EB and minus root EB. For symbol 1 is represented by root EB and symbol 0 is represented by minus root EB. Why? These are the antipodal signals. So S1 of t is nothing but root EB pi 1 of t. S2 of t is minus root EB pi 1 of t. So this pi 1 of t is the basis function which can also be used as a phase. So for the coherent detection means if I am using the same phase value for recovering the message signal at the receiver, then it can be called as coherent detection. So similarly, this can be called as a signal space diagram or signal constellation diagram. So similarly, at the receiver also, we are having the observation space. So this is also pi 1 of t. But here the total observation space is partition along with the decision boundary. Okay. So x1 is the observation vector, which is taken from the x of t. So we are going to integrate x of t, pi 1 of t, we got the x1. So now when symbol 0 is transmitted, the maximum likelihood function. Why? Because the probability of error of any decision modulation technique can be measured by the error complementary function. So the error complementary function is also a function with the maximum likelihood function. So first we start from the maximum likelihood function. So the maximum likelihood function can be represented as f suffix xj of xj conditional to mi, which is equal to 1 by square root of pi n naught exponential of minus xj minus sij whole square by n naught. So xj. So xj is what you receive that observation vector. Here x1. So I can replace this xj with x1. Why? J, which indicates the basis functions. How many basis functions are required for representation of the signal at the transmitter? So here I require only one basis function, that is pi 1. So j is equal to 1, 2, and it is nothing but represents the basis function. And I is equal to 1 up to m and j equal to 1 to n. Okay, so j represents the number of basis functions, I represents the number of signals. Okay, so number of signals, for example, here you take the signal space diagram or constellation diagram. Here, this are S1, 1, S2, 1. S11 means here symbol 1 is transmitted. That is nothing but root EB pi 1 of t. But in the constellation diagram or signal space diagram, we represent this root EB as S11. That means the first signal project on the first basis function, that is S11. And another one is the S21. That is the second signal projected on the first basis function, that is S21. So that notation is used here, Sij. In the first function of maximum likelihood function, exponential of xj minus Sij whole square. Here xj is a what observation vector you receive, that is minus Sij, that is a signal vector. So here what I am sending, when 0 is transmitted, the maximum likelihood function. Here I am going to write. So again rearrange this maximum likelihood function as f suffix x1. Why? My j is 1. Only one basis function. So here j value is 1. So x1. So mi is the symbol which message symbol we sent. Here what I send, the symbol is 0. So 0 is sent. And the right hand side, which is equal to 1 by square root of pi and not is the spectral density, exponential of minus, in place of j value is taken as 1. So x1 minus Sij. Here Ij is the 21, S21. Why? In the signal space diagram, S21 represents the 0. If 1 is transmitted, it may be S11. Here what I am saying, when symbol 0 is transmitted, so here I am transmitted 0. So in the constellation diagram, S to 1 it is going to represent. So that's why for 0 representation it is S to 1. So that's why x1 minus S to 1 whole square by N naught. So the conditional probability of receiver makes decision in favor of 1 given symbol was transmitted. So that's the error is rise. What is transmitted? 0 is transmitted. But what the receiver makes decision? In favor of 1. So here we got the error. That is the probability of error. P 0. So 0 means 0. Symbol 0 is transmitted. So how much error we got? So P0 is equal to 0 to infinity f of x1 conditional to 0 dx1. So here we are using that maximum function. We are integrating that maximum function simply. So that is equal to 1 by square root of pi n naught integral 0 to infinity exponential minus x1 plus root eb whole square divided by n naught dx1. Why? Because here what do you return? Exponential minus xj minus s to 1. Here in the previous, what do you return? Integral exponential minus of xj is x1 minus of sij. Here sij is s21. So s21 whole square divided by n naught. So here what is s21? That is minus root eb. Already shown in the signals diagram. So minus of minus is nothing but plus. So x1 plus root eb whole square divided by n naught into dx1. So this is my probability of error. First symbol 0 was transmitted. Now for simplification, I taken let z equal to x1 plus root eb divided by root n naught. Why here I am going to find this probability of error. So for simplification purpose, let z equal to x1 square root of root eb by root n naught. And I am going to change the differentiation also. Why? In integration dx1 is there, no? So I am going to change this dx1 into dz. So for that, differentiate on both sides. Then it is converted as a dz is equal to dx1 by root n naught. I am changing the limits also. But what is that ERFC? Error complementary function of u, which is equal to 2 by root pi integral u to infinity exponential minus z square dz. So this is the original error complementary function. Okay. So we are taking the probability of error, that is conditional probability, which is equal to integral here u. What is u? That is nothing but root eb by n naught. Why? Because here substitute a 0 value in the above z equal to x1 plus root eb by root n naught. So x1 is 0. So what you get? Root eb by n naught. That is the lower limit, and the upper limit is infinity. So if we place infinity, it must not get the infinity. And lower upper limits are placed. And the remaining 1 by root pi e power minus z square. Why? In previously written, it is exponential of minus of x1 plus root eb by n naught. So we replace it. That value is with z. So that's why this is changed as exponential minus z square dz. Now, so this is the probability function, conditional probability function, and ERFC formula. That is ERFC is equal to 2 by root pi integral u to infinity exponential minus z square dz. So finally the probability error of symbol 0 is equal to 1 by 2 ERFC of root EB by N naught. This is for PSK phase shift key. So again we take this one, probability of error. Here rearranging, we are rearranging, so that's why it gets ERFC of u. What is u? Here root of root EB N naught. Okay, so this is the probability of error of PSK phase shift key. And another one is probability of error of FSK. So for understanding of this probability error of FSK, we are again remember that the receiver, how the receiver works in FSK. So in the receiver we are having two channels, upper channel and lower channel, and the upper channel is linked with one of the basis function and this one. So here I got two outputs getting, that is x1, x2. Why? Because at the receiver we are having two basis functions are used, whereas in PSK I use only one basis function. Why? Because it is antipodal signals, but in FSK it is orthogonal signals. Why? Because once again we go for the signal space diagram. Here this is pi 1 of t and this is pi 2 of t, and here we can represent these two. So this one is S1 of t, or you can say root EB, directly the energy of that symbol, and this is 1 and this is represented for symbol 0. This is also root EB. Why? Here there is no minus symbol. There is no minus symbol. Why? Because I use two basis functions. That means here J value, the J value is 1, 2 and I value also 1, 2. Okay. Why? Because two symbols and two basis function are used to represent of this FSK. Why? S1 of t, here S1 of t is nothing but root EB pi 1 of t. S2 of t is equal to root EB pi 2 of t. So this is the representation of the FS signals. You can see at the transmitter. At the transmitter we are getting these two signals. Now here we are taking L. L is equal to x1 minus x2. Why? The difference here we are taking. This is L. So x1, x2. Here also we are getting observation vectors. So that L value is equal to x1 minus x2. So for understanding purpose of probability of error, we must go to the receiver. Through the receiver you can easily understand. So once again you can see this receiver diagram, then you can easily understand this probability of error, how it is going to solve. Okay. So symbol 1 was transmitted, x1, x2 have mean values equal to root EB and 0 respectively. The conditional mean of the random variable is L. So here it is equal to root EB and 0, where when symbol 1 was transmitted. So the conditional mean of the random variable is L. So here the conditional mean expression of E L conditional to 1, which is equal to expression x1 conditional to 1 minus expression x2 conditional to 1. So if x1 symbol 1 is transmitted, its value is root EB, and for x2 it is 0. So that's why root EB minus 0 is got root EB. when it is symbol 1 was transmitted. And symbol 0 was transmitted, x1 and x2 have mean values equal to 0 and root dB respectively. So the conditional mean of the random variable L is, so expectation L is conditional to 0, that is equal to expectation x1 conditional to 0 minus expectation x2 conditional to 0. So what the condition first? If x1 is 0 and x2 is root dB. So here just go to substitute these values, then symbol 0 was transmitted, this conditional mean value is minus root dB, whereas 1 was transmitted, it is root dB. Okay. Then each random variable has a naught by 2 variance. So here you are considering the mean value and the variance. Now I am going to add these two variances. So variance of L is equal to variance of x1 plus variance of x2. So each random variable has a naught by 2. So a naught by 2 plus a naught by 2. So simply it is a naught. So the variance of L is equal to a naught. Whereas mean of L value for symbol 1 is transmitted is root dB, and mean value of L for symbol 0 is transmitted is minus root dB. Now the conditional probability function of random variable L is f suffix L random variable L conditional to 0, which is equal to 1 by square root of 2 pi n naught exponential of minus L plus root dB whole square by 2 n naught. Why this is changed for the previous one? Here in the previous one, we are having only one observation vector, that is xj you represent. But here it is a combination of two vectors, that is L is equal to x1 minus x2 we represent. Okay, so that's why we taken this value is L. Okay, and remaining all are same to same. And another one is, whereas the previous one we're having this a naught, but here to a naught. Why? The variance of L is equal to a naught here. Okay, so that is the difference you can observe. So here also same symbol 0 is transmitted, but the receiver makes a decision in favor of symbol 1. So we got the probability of error. So that's why we got the error. So that error we are going to find. Again the same formula, that is equal to integral 0 to infinity FL of random variable L conditional to 0 dl. Okay, so we are rearranging according to our problem. Okay, so here the first equation, conditional mean function, the conditional probability function, which is equal to 1 by square root of 2 pi n naught integral 0 to infinity exponential of minus L plus root dB whole square by 2 n naught dl. So here also let z is equal to L plus root dB divided by root of 2 n naught, that is z. So here I am changing this values. Okay, so that's why I taken z, and here it is in the form of dl, so the derivation is changed to z. So I am going to differentiate both sides, so that the left hand side is a dz and the right hand side is a dl by root n naught. So root dB is 0, no need to integrate this one, it's treated as a constant. Root dB is nothing but energy per bit. Okay, so after we are going to substitute these values in the probability of error. So this is also probability of error. Okay, probability of error for symbol 0. So Pe naught, which is equal to 1 by square root of 2 pi n naught, and the lower value is u, So that is nothing but root EB by 2 n naught. Why? Here substitute the 0 value. Here the L value is 0 and finally what remaining? That is square root of root EB by 2 n naught. So that's why here root EB by 2 n naught and the upper limit is infinity as usual and exponential of. So this total term I treat it as Z. So minus Z square. And what is the DL value? So DL is taken from here. DL is equal to DZ square root of 2 n naught. So here I am going to substitute this DL value. So numerator having square root of 2 n naught and the denominator also having square root of 2 n naught. So these two is going to cancel. Okay. So what is the remaining? 1 by square root of pi, 1 by root pi, integral square root of root EB by 2 n naught, exponential of minus Z square dz. So here we are going to use the error complementary function. So probability of error for symbol 0 is equal to integral square root of EB by 2 n naught infinity 1 by root pi exponential minus Z square dz. So I am going to rearranging this probability of error in terms of error complementary function. So probability of error is equal to 1 by 2 RFC of square root of EB by 2 n naught. So what the difference you are getting for the probability of error for PSK to FSK is only this two term. These two. So remaining all are same. That means square root of root EB by n naught. As usual in PSK also. Okay. And next we go for the probability of error of ASK. So here also same the procedure. What you take in? We take in the maximum likely function, that is f of x1 0 conditional to 0, that is equal to 1 by square root of 2 pi sigma square in exponential minus x1 square by 2 sigma square. So sigma square is nothing but n naught by 2, whereas previously we directly used this n naught by 2, but here we taken as sigma square. So don't confuse. So when you substitute in this equation sigma square, so n naught by 2 goes to square root of pi n naught as usual. Exponential of minus xj minus sij whole square. So this related to the basis function and this related to the signal vector. So probability of error for symbol 0 is equal to integral x1 d by 2 integral x1 is equal to d by 2 to infinity f of x1 conditional to 0 dx1. Here also symbol 0 was transmitted. Symbol 0 was transmitted. So this is the first and second equations. So let z equal to, here also let z equal to x1 by root 2 sigma and z square is equal to x1 square by 2 sigma square. That means for rearranging I am going to square, but now previously we not do like that. Previously not used like that. So that's the equation is different. So here the sigma square is k. So that's why some changes. And here also we changing the limits. So the integration changing, the differentiation also changing. So let z we taken. So we are going to differentiate. It is dz, that is equal to dx1 by square root of 2 sigma. And our error complementary function ERFC of u, that is equal to 2 pi root pi integral u to infinity exponential minus z square dz. So this is the basic or main error complementary function. So by using this main function, we are going to change it. This is the main equation. Error complementary function is the main equation. Simple. So the probability of error, which is equal to integral z equal to d by 2 root 2 sigma to infinity 1 by root pi exponential minus z square dz. So here the remaining is same. That is what you seen in the right hand side for the error complementary function to the maximum likely function. The right hand side is both same. But what is the difference? Here only these two. So when you move this 2 to the left hand side, what you got? So nothing but 1 by 2. So that's why the probability of error is equal to 1 by 2 error complementation of u. So that's we're getting. So I'm going to equating those two equations. So the probability of error is equal to 1 by 2 of error complementary function of u. So what is u here? D by 2 root 2 sigma. Okay. So this one. Probability of error is equal to 1 by 2 ERFC of D by 2 root 2 sigma. So this is my u. So again rearranging the sigma value, that is a naught, simply got. So the distance here goes substitute, it is root EB. So finally the probability of error for ASK is equal to 1 by 2 ERFC, error complementary function of root EB by 4 and naught. So here again increased another 2 for PSK, FSK, ASK. So PSK, FSK and ASK. So here root EB by n naught, root EB by 2 n naught, root EB by 4 n naught. So thus you can see. So the error complementary function. So remaining is same 1 by 2 ERFC. So that's I'm not speaking about. But in this error complementary function of square root of root EB by 4 net. So here it is going to increasing like this. This T2 value increase in denominator. Okay. So here this total content is taken from the communication systems by Simon Hacking textbook and digital communication by Simon Hacking. So totally this information is taken from the Simon Hacking. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.